The nexus where quantum mechanics intersects with the enigma of consciousness remains perhaps the most profound and stubbornly opaque frontier in contemporary scientific inquiry, a liminal space where the rigorously defined laws of the subatomic world brush against the subjective, irreducible experience of being. This intersection, often dubbed the quantum consciousness problem, is not merely a philosophical curiosity but a potential cornerstone for a unified theory of reality, one that might finally bridge the chasm between the physical substrate and phenomenal awareness. To delve into this area is to navigate a landscape littered with paradoxes, supported by increasingly sophisticated, albeit speculative, theoretical frameworks and tantalizing, yet often contested, experimental hints. The foundation of this discourse rests squarely upon the inherent strangeness of quantum mechanics, the theory that governs the behavior of matter and energy at the atomic and subatomic levels. Central to this strangeness is the principle of superposition, where a quantum system exists in a probabilistic combination of all its possible states simultaneously, a concept famously illustrated by Erwin Schrödinger's thought experiment involving a feline existing in a dual state of being alive and deceased until an observation forces a probabilistic collapse into one definitive state. This collapse, the transition from potentiality to actuality, is mathematically described by the wave function, represented by the Greek letter psi, which evolves deterministically according to the Schrödinger equation, yet yields inherently probabilistic outcomes upon measurement. The measurement problem, therefore, becomes the initial critical juncture: what constitutes a measurement, and what is the physical mechanism responsible for this seemingly instantaneous, non-local transition from the quantum realm of indeterminate possibilities to the classical realm of definite outcomes we perceive. For decades, interpretations of quantum mechanics have grappled with this transition. The Copenhagen interpretation, historically dominant, posits that the act of observation, implying the involvement of a conscious observer, causes the collapse. This places consciousness at a fundamental, if poorly defined, role in shaping physical reality, a notion highly appealing to those seeking to link the observer effect directly to subjective awareness. However, proponents of the many worlds interpretation, advanced by Hugh Everett III, offer a radical alternative. In this framework, the wave function never truly collapses. Instead, every possible outcome of a quantum measurement is realized in a separate, branching universe, forming an ever-proliferating multiverse. Consciousness, in this view, merely follows one specific branch, experiencing only that particular reality, thus circumventing the need for a privileged role for the observer's mind in collapsing the wave function. Yet, the sheer ontological extravagance of infinite parallel universes presents its own set of formidable conceptual challenges, particularly regarding conservation of energy and the mechanism of branching itself. The debate intensifies when considering decoherence, the modern scientific mechanism frequently invoked to explain the transition from quantum weirdness to classical experience without resorting to consciousness. Decoherence describes how a quantum system rapidly loses its quantum coherence, its ability to maintain superposition or entanglement, due to interaction with its environment, typically thermal agitation or stray photons. The environment acts as a vast, complex measuring device, effectively sampling the system's state across many degrees of freedom, causing the off-diagonal terms in the density matrix, which represent quantum correlations, to rapidly decay towards zero. This process is remarkably fast. For macroscopic objects, decoherence occurs on timescales vastly shorter than a femtosecond, which intuitively explains why we do not observe cats simultaneously dead and alive. However, decoherence, while explaining the appearance of classicality, does not fundamentally solve the measurement problem. It merely pushes the question back a stage. The resulting state, after decoherence, is often a statistical mixture of classical possibilities, but the question of which specific classical reality is experienced remains unanswered unless one adopts a specific interpretation of what the decohered state represents, a mixture or a definite outcome. This unresolved tension forms the fertile ground for quantum consciousness theories. If the brain is fundamentally a classical machine, operating via electrochemical signaling governed by classical physics, then consciousness, in its rich, subjective phenomenal unity. The qualia of seeing red or feeling pain must be an emergent property of complex classical computation, akin to how wetness emerges from vast collections of water molecules. But critics argue that classical emergence fails to account for the binding problem. How do disparate neural activities across different cortical areas integrate instantaneously into a single, unified conscious field? Why is my perception of a bird flying not experienced as separate inputs for color, shape, motion, and sound, but as one seamless event? It is precisely here that the quantum realm offers a tantalizing, if highly speculative, escape route. Proponents argue that if the physical substrate of consciousness operates at a sufficiently fine scale where quantum effects are non-negligible, then phenomena like superposition and entanglement might provide the necessary non-classical mechanisms for the instantaneous, unified processing required by subjective experience. The most influential, and controversial, theory in this domain is orchestrated objective reduction, or OR, proposed by physicist Sir Roger Penrose and anestheologist Stuart Hameroff. Their hypothesis posits that consciousness arises from quantum computations occurring within the microtubules, dynamic protein polymers found within the cytoskeleton of every neuron. Hameroff observed that the geometry and tubulin protein subunits of microtubules exhibit structural features suggestive of quantum coherence, potentially allowing them to sustain quantum states longer than the surrounding warm, noisy cellular environment. Penrose, bringing his background in general relativity and mathematical physics, proposed that the actual reduction of the wave function, the selection of a definite state, is not random or dependent on an external observer, but is an instance of objective reduction, and non-computable self-collapse driven by a threshold related to the spacetime geometry arising from the mass-energy differences inherent in superposed states. This threshold is described by a modified version of the Schrödinger equation incorporating quantum gravity effects, hence objective reduction. When this objective reduction occurs within the microtubule network, it generates a moment of proto-conscious experience. The orchestration part refers to the hypothesis that synaptic inputs modulate these quantum processes, effectively tuning the moments of conscious experience. The theoretical elegance of Orch lies in its attempt to address multiple long-standing problems simultaneously: the measurement problem, the binding problem, and the hard problem of consciousness, explaining why physical processes give rise to subjective experience. Penrose suggests that these quantum gravity events access a fundamental, non-computable layer of reality, suggesting consciousness is not merely an information processing function but a direct manifestation of the universe's intrinsic structure. However, Orch faces substantial scientific hurdles, primarily related to the issue of environmental decoherence. The brain operates at a warm, wet temperature of approximately 310 Kelvin. Conventional wisdom dictates that quantum coherence at this scale should be obliterated almost instantaneously, far too quickly to support the complex, integrated computations necessary for conscious thought. The timescale for thermal decoherence in such an environment is often estimated to be on the order of 10 to the negative 20th seconds. Hameroff and his collaborators counter this by referencing theoretical work suggesting that the highly organized, crystalline-like structure of the microtubule lattice, possibly shielded by associated proteins and ordered water layers, could facilitate a phenomenon called protection from environmental noise or even exploit quantum effects like environmentally assisted quantum transport, similar to what is hypothesized in highly efficient photosynthesis. Some studies have hinted at transient, non-trivial quantum effects in biological systems, such as enhanced energy transfer in photosynthetic reaction centers, providing indirect, albeit non-conclusive, support for biological quantum coherence persisting longer than traditionally assumed. For instance, studies utilizing two-dimensional electronic spectroscopy have provided evidence suggesting quantum coherence effects playing a functional role in energy transfer in certain bacterial light harvesting complexes, operating at ambient temperatures. The debate rages on, Is the brain merely utilizing classical approximations of quantum processes, or are genuinely sustained, functional quantum computations occurring within specific neural structures? Beyond microtubules, other quantum consciousness models explore different biological candidates. Some theories focus on quantum effects within the lipid bilayer of neuronal membranes, suggesting that fluctuations in ion channel gating, the opening and closing of protein pores that control neuronal firing, might be quantum mechanically determined, influencing the probabilistic nature of synaptic transmission. The precise alignment and conformational dynamics of these channels involve energy differences small enough that quantum tunneling might play a role, especially given the precise temporal resolution required for spike timing-dependent plasticity. Another avenue explores quantum entanglement operating across distant regions of the brain. Entanglement, the bizarre correlation where two or more quantum particles remain linked regardless of the spatial separation between them, offering instantaneous correlation between their measured properties, is an essential resource in quantum computation. If significant entanglement could be maintained between spatially separated neurons or even across different neural populations, it could offer a physical mechanism for the instantaneous binding of disparate information streams that characterize unified perception. The challenge remains demonstrating entanglement survival in the noisy, high-temperature context of the living brain for timescales relevant to cognitive processing, which often spans milliseconds to seconds. Current research in biological quantum physics is slowly starting to probe these possibilities, often using highly sensitive magnetic resonance techniques, though definitive evidence of large-scale, functional quantum entanglement in the operational brain remains elusive. The philosophical weight of quantum mechanics on consciousness extends beyond specific physical mechanisms into the very nature of information. Information theory, particularly in its intersection with physics, suggests a deep connection between the physical substrate and informational content. In classical physics, information is represented by bits, physical states that are definitively 0 or 1. In quantum mechanics, information is encoded in qubits, which can represent 0, 1, or a superposition of both. If consciousness is fundamentally an information processing phenomenon, as suggested by strong proponents of integrated information theory, or IIT, developed by Giulio Tononi, then the vast computational space afforded by quantum information, with its exponential increase in representational power through superposition and entanglement, might be necessary to account for the sheer richness and complexity of conscious experience. IIT attempts to quantify consciousness by calculating the amount of integrated information, denoted by the Greek letter phi, $, within a system, the degree to which the system's current state constrains its past and future states in a way that is irreducible to the sum of its parts. While IIT is primarily framed in terms of classical, causal structure, some theorists propose that quantum degrees of freedom, if integrated, would dramatically enhance the potential $phi value of a system, potentially linking high $phi values to genuinely conscious experience. The concept of non-locality inherent in quantum entanglement also echoes certain aspects of consciousness that defy classical explanation. Quantum non-locality suggests that influences can correlate faster than light, although this cannot be used to transmit classical information faster than light, due to the probabilistic nature of measurement outcomes. Philosophically, this mirrors the subjective sense of instantaneous awareness across the entire field of consciousness, rather than a sequential, piece-by-piece assembly determined by the speed of neural transmission across the cerebral cortex. Could quantum non-locality offer a substrate for the holistic nature of awareness? The scientific community remains highly polarized on the validity of quantum consciousness theories. Critics, often adherents of strong emergentism or computational functionalism, argue that invoking quantum mechanics is an appeal to mysticism, often dubbed quantum woo. They point out that, while quantum mechanics governs the behavior of fundamental particles, the brain, at the scale of neuronal activity, the firing of action potentials, the release of neurotransmitters, operates overwhelmingly in the classical domain. The process is relevant to psychology, and cognition occur over timescales of milliseconds to seconds and involve thousands of particles interacting, a regime where, according to the laws of thermodynamics and decoherence theory, quantum coherence should be instantly washed out. Critics emphasize that an explanation requires demonstrating a functional role for quantum effects, not just observing that quantum physics underlies all chemistry and biology. They demand a concrete, testable prediction that classical neuroscience cannot account for. In response, quantum consciousness advocates point to the limitations of current models. Classical models, they argue, struggle profoundly with the qualitative aspect of subjective experience, the what it is like aspect. If the brain is just a classical Turing machine, albeit a complex one, then any computation it performs should, in principle, be simulable by a classical computer. Yet, the subjective experience of consciousness feels fundamentally non-algorithmic, non-computable in the classical sense. Penrose argues that human mathematical insight and ingenuity demonstrate capabilities that go beyond any formalized algorithmic procedure, suggesting an access to non-computable realities, which he anchors in the objective reduction events facilitated by quantum gravity. The search for empirical evidence has been tentative and fraught with difficulty. Experiments attempting to detect quantum effects in biological molecules are challenging because the signals are incredibly weak and susceptible to environmental noise. One area of active investigation involves exploring whether anesthetic gases, which reversibly abolish consciousness, act by interfering with quantum processes in the brain. Anesthetics are known to interact with hydrophobic pockets in certain ion channels, but Hameroff suggests their mechanism might be more fundamental, perhaps disrupting the delicate quantum coherence required for protoconscious events within the microtubules, effectively silencing the quantum computation without stopping all classical neural activity. If a specific class of molecules reversibly turns off consciousness by interacting with a hypothesized quantum substrate, this would constitute significant, albeit circumstantial, evidence. Furthermore, the study of certain neurological conditions or states, such as dreaming or psychedelic experiences, might offer windows. During rapid eye movement sleep, the brain exhibits high-frequency electrical activity similar to wakefulness, yet subjective experience is profoundly altered. Could changes in the environment of cytoskeletal structures during different sleep stages modulate quantum informational processing? Similarly, psychedelics dramatically alter perception and selfhood. Their known molecular targets often involve serotonin receptors, but the extent to which these interactions propagate to non-classical levels of brain function remains entirely speculative. To push the boundaries of this research, future directions must focus on developing more sophisticated experimental techniques capable of probing quantum phenomena in vivo, at physiological temperatures, and within biologically relevant timescales. This necessitates the development of ultra-sensitive quantum sensors capable of detecting subtle changes in spin states or entanglement signatures within neural tissues, perhaps utilizing advancements in nitrogen vacancy centers in diamond microscopy adapted for biological interfaces. Theoretically, the pursuit requires refining models that bridge quantum field theory, general relativity, for Penrose's OR component, and complex systems biology, creating a mathematically consistent framework where classical emergent phenomena transitions smoothly from quantum underpinnings, respecting physical laws while accounting for subjective experience. The concept of protoconsciousness is also crucial here. Many theorists suggest that consciousness, rather than emerging fully formed from complex organization, might be a fundamental property woven into the fabric of reality, perhaps associated with space-time geometry or basic quantum events, as suggested by interpretations like those stemming from panpsychism, albeit often infused with quantum mechanical descriptions. If reality possesses protoconscious properties at the Planck scale or during quantum reduction events, then biological structures like the brain do not create consciousness but rather organize and amplify these pre-existing fundamental properties into the complex, structured experience we recognize. This perspective elegantly sidesteps the hard problem by proposing that the physical and the experimental are two sides of the same ontological coin. The implications of a confirmed quantum link to consciousness are staggering. If consciousness is fundamentally quantum mechanical, it suggests that reality is inherently non-local, non-deterministic, and perhaps not entirely reducible to classical computation. This could revolutionize artificial intelligence. Current AI models, based on classical neural networks, may fundamentally lack the capacity for genuine subjective awareness, no matter how complex their architecture, because they lack the underlying quantum substrate. A truly conscious AI might require hardware based on quantum computation, not merely running quantum algorithms on classical hardware, but systems capable of harnessing genuine objective reduction or sustained entanglement relevant to their architecture. Conversely, if rigorous experiments definitively rule out any functional role for quantum mechanics beyond standard chemical bonding and thermodynamic considerations in generating consciousness, then the hard problem remains squarely within the domain of classical neuroscience and philosophy of mind, perhaps demanding a radical shift in our understanding of emergent properties in complex classical systems. A shift as profound as the shift from Newtonian to Einsteinian physics, but confined to information processing rather than spacetime. The ongoing narrative at the quantum consciousness intersection is one characterized by deep uncertainty, immense potential, and rigorous intellectual debate. It forces us to confront the limits of reductionism and the very definition of physical reality. Whether the secret lies hidden in the subtle dance of tubulin dimus, the entanglement across the corpus callosum, or in some yet-to-be-discovered fundamental aspect of quantum gravity dictating the collapse of potentiality into lived experience, the pursuit continues, driven by the profound human desire to understand the source of the I that observes the universe, a pursuit where the mysteries of the smallest possible scales meet the most intimate reality of subjective existence. The successful decoding of this juncture promises not just a new chapter in physics, but perhaps the ultimate answer to what it means to be. The sheer difficulty stems from the fact that consciousness is both the subject and the object of the investigation, the instrument measuring the very phenomenon it seeks to measure, a self-referential loop that physics has never before successfully navigated.